no, dude.
I don't think it.
All right. So number 1 says, find the volume of the solid formed by revolving the region bounded by the graph of cosine of x and the x-axis on the interval, the x-interval technically, 0 to pi over 2, if that's revolved around the y-axis. There's a little typo in here. I think if you take away the words is revolved, then I think it makes grammatical sense. So what we're going to do is we're going to graph this on paper, and then I'm going to have you try to create it with the Play-Doh. So here is the y-axis, here is the x-axis, and the graph of cosine. Does cosine normally start in the middle or high?
High.
Normally starts in the high end, right at the top of the amplitude. So cosine would start up here.
It's not showing.
It's not shown.
Oh, it's not? Why is it not showing? That seems odd. It's right there.
That might help.
Wow, that's really strange. There's the region that we were talking about. And this is the interval from 0 to pi over 2, revolving around the y-axis. You guys have had a chance to do the Play-Doh here. I haven't seen them all. I'm looking around. I'm seeing some good stuff. If you were to try to describe what this region looks like, it gets revolved around, creates this solid, how would you describe this region? What would you call it?
Looks like a dot candy.
Oh, a dot candy. You guys know what that is?
Yes.
Pretty good description.
Oh,
Yeah.
true.
Often at the movie theater, right?
Yes.
Yeah. The dot candy. For those that are like hunters or whatever, I always picture like, this looks like a bullet.
Yeah.
Not like the bullet inside the shell, but just like the bullet that actually comes out the end of the gun. Kind of looks like that a little bit. But yeah, I'm going to adopt the dot candy. I think that's a pretty good representation. Yeah.
Why do you say revolved around instead of just reflected?
So, yeah, that's a good question. So what it is, can I give you, I've got another little demo here. It's not going to make for a very good video, but revolved around means, I think I've got a demo, I wasn't planning on doing this, but here we go. So, yeah, so when we say revolved around, what we want to think of is we want to think of a region like this, right, kind of like what you see there, with this being the y-axis. Like if you take that region and you open it up like this, like all the pages in a book, like all those little pages, this one is kind of reclosed on me a little bit, all the little pages would kind of leave like a reflection or like an image of themselves. And so as you like open this book all the way, and it's not going to work very well because it's been a while since I got this out, but these pages would spread out, and as you revolve it all the way around, the pages would kind of fan out and create this 3D, I'm not doing a very good job demonstrating, but I can see you're starting to get it. That kind of shape, and those pages would be like a little image left over as it revolves around. Okay. Good question. Anybody else with a question? Okay. So if you would, you've all done a nice job. You got the axis of rotation in there. It all looks really good. Take your Play-Doh, set it off to the side, take your pencil back out if you use that. We're going to do a little bit of work, and we're going to try to find the actual volume of this shape. So a little bit of remembrance from the video. We are going to be using what's called the disk method here. And with the disk method, and really with any of these methods of finding solids of revolutions volume, this statement will always be true. Let's see if you can finish my statement. The representative rectangle should always be blank to the axis of rotation.
Parallel.
It's the exact opposite. The axis of rotation and the representative rectangle should always be perpendicular if using what we're going to be using here, the disk method. There is an alternative method where what Drew said is true, but we are not going to be covering that. It's not something we have to, so it's something that we won't. And so this representative rectangle needs to look something like that because it needs to be perpendicular to our axis of rotation. For you guys in this class, for all the problems that we'll do, that perpendicular relationship will always be the case. But again, full disclosure, there's a different method where that's not the case, but for us, this is what we're going to stick with. So, because it's a representative rectangle like that, I would call this a horizontal representative rectangle, that really sets in motion everything else. What is the thickness of that representative rectangle? dy. The reasoning behind that is, if you look at that rectangle, the length of it is going to vary depending on whether it's on the upper end of the region or on the lower end. It's going to go from short to long or whatever. But the thickness will be consistent. The thickness is like a little itty bitty change in y. Notice what I'm doing with my hand. I'm moving it up and down, right? The thickness is measured like this, a little tiny change in y. That's why we call it a dy thick or a dy rectangle. So I'm just going to make a little note of that and say, hey, this is dy. And what that sets in motion is that means whenever I write my integral, for us, it means that every single variable, every single item within that integral will have to be in terms of y. And that might pose some challenges at times, but we can deal with all of them if they happen to come up. So here's how we do this. You guys maybe remember from your video and from your quiz before, volume is equal to pi integral of radius squared dx or dy. And since it's a dy, I'm going to go ahead and put dy right there. Listen, I've been doing this for a really long time. I've been doing calculus in some form or fashion since 1992. And so you would think that, given any question like this, I should just be able to do it immediately in my head with no form of thought or at all. But the truth is, if I want to make sure that I get it right, like if I'm doing one of your quiz keys or I'm doing some AP question or one of you asked me a question and I want to be for sure that I get it right, as soon as I identify that it's this method, I'm going to write something like that down. I have not written down what the limits are or what the integrand is specifically, but I know it's going to be pi integral something squared dx or dy, and now we'll fill in the details. Does that make sense? So I always try to give myself this framework where I can say, okay, I know it looks like this, now I'm going to try to fill in all the right details. So here we go. Because it's a horizontal representative rectangle, it's going to accumulate from, you pick, right to left or bottom to top? Bottom to top. It's going to accumulate like this. So a vertical representative rectangle will accumulate from left to right, side to side. A horizontal will accumulate from bottom to top, up and down. Okay, so with that in mind, the accumulation pattern has to go with my limits of integration. So where am I going to start accumulating? 0. And where do I stop? 1, right? So from 0 down here at the top of the region would be at 1. You'd be tempted to put pi over 2, but that's the wrong direction of accumulation. So 0 to 1 goes here. And now we'll finish with the more challenging thing, and that is the radius. You've known for a long time that the radius, isn't that just simply the distance from the center of the shape out there to the outer edge? Right? And you can see that my representative rectangle does an okay job of representing that. It says, hey, we start there at the center of our shape where your pencil was, right? And then we go all the way out there to the outer edge. And so how do we express that, though? Because let's be honest, depending on where you are in the region, the length of that radius is going to be different. When you're at the very bottom, it's going to be longest. And when you're at the top, it's going to be nearing 0, isn't it? So depending on where you are in the shape, it's going to be a different radius. So here's how I would want you to think about this, or here is a way to think about it. If I put a dot over here on the axis of rotation, the center of the shape, and then another dot out there on the outer edge, and I draw a line between, that would again represent the radius. Let's think about what that is. Go back to your, 6th grade, maybe 7th grade days, when your teacher first taught you about graphing, and your teacher said, essentially, if you start kind of like there on the origin or on the y-axis and you move to the right, what do we call that distance? If you start at the y-axis and move over to the right?
X.
Isn't that specifically x? Isn't that what that is? The distance from the axis of rotation out there to the outer edge. Literally, the radius is just x. It's whatever the x coordinate is, that's the length of the radius. So you might think, all right, cool, I'm just going to go ahead and put an x right there. And really, conceptually, you're correct. But as far as moving forward and getting an answer, it's not what we want, is it?
No.
But it's still true. X is that distance. And so really the question becomes, if everything has to be in terms of y, which is true for this to actually work out, what could I do to replace that x with something equivalent to it that only has y's?
So what could it y?
Solve for what?
Like when y equals x, couldn't you just solve for y?
Y equals x? Where are you getting that?
X.
So in this equation, no.
I don't think y equals x. I don't see that anywhere.
Okay.
Y equals
Okay.
cosine, right?
Yeah.
Oh, but y equals cosine of
Then
x.
solve for x and then plug whatever.
Oh, now we're talking. So if y equals cosine of x, which is what is said right here, then we could say, well, if y equals cosine of x, I could solve for x. How would I get the x by itself? Yeah, I heard somebody say inverse cosine. That's right. So inverse cosine of y is equal to x. So then what I could do then is say, oh, you know what, that x was true, but it's not the form that I wanted. I could replace it with inverse cosine of y. Now, if this were a quiz question and I wanted you to actually get an answer for this, it would definitely be calculator active. So I'd be looking for you to set that up as such, write it down, and then turn to Math 9 on your calculator to help you get there. Will you do that? Will you guys take your calculators out, do Math 9? Let's actually find the true volume of this. I think it's always a good idea to practice the technology. One of the most commonly forgotten things in these situations when you turn to the calculator, sometimes when you write it down, is pi. So I'd encourage you to do this. When you enter this in your calculator, type this in exactly like this. Pi Math 9. And then put in the other stuff. If you think that you're going to remember to multiply by pi in the end, you probably will, but there will also probably be a time when you forget it. So if you always go pi Math 9, then I think it's less odds, that you'll make the mistake of forgetting the pi. So once you got an answer, let me know.
Did you just replace the y's with x's?
So yeah, when you go inverse cosine of something and you push like your variable button,
Yeah.
it's going to show up as an x. But then you'll also do dx, and so we know that those are y's, but your calculator is going to treat them like variables. So that'll still work out okay.
Do I put the square right there? Or you just do all
No,
of
because
it?
it's only squaring dx. I would open a parentheses in front of
Okay. I'll put
the
it
inverse
on the whole
cosine
thing.
and then close it around the backside and then put your squared there. I think I remember the answer to this. Anybody mind sharing?
I got
2.28. And now that you say that, I can't remember if that's it.
I did not get that.
What did you get, Mandy?
I got 3.586.
3.586? That sounds familiar. So let's go with that. 3.586. Alyssa, they were kind of shouting you down. Alyssa, two things.
I accidentally put cosine instead of cosine.
Okay, there you go. People often forget the squared as well, so that happens. Okay, do you guys have any questions about that? How to do it? Any surprising results? Or
Why couldn't we just solve for x? Why couldn't we just do dx?
we did solve for x.
Why couldn't we, solve, why couldn't we put the,
Like leave the x in there?
yeah.
So for us in Calculus 1, which is essentially what this is, we can only do, if you look at the cover of your book, it's called Calculus of a Single Variable, I think. Or maybe I'm thinking of a different book. So at this point, our skill level only allows us to do the calculus of a single variable. So if you have an x right here, there's really nothing wrong with that, but this has to be a dy. So to do the integral of x dy, now you're doing the integral of multiple variables. It calls on totally different techniques.
Why couldn't that be dx instead of dy?
Okay, good question. Because in order to use the disk method, which is all you know how to do yet at this point, all that you will know how to do as far as this type of shape, you have to use a horizontal representative rectangle. Has to be perpendicular to the axis of rotation, and that means that the thickness is dy.
Okay.
If it was vertical, it would be a dx rectangle. But that's why I said at the start that if we have to use a horizontal representative rectangle, that sets us on a very specific path. If we're going to be using dy, that means that in the end, everything has to be in terms of y. Everything. For it to work out for us. Because we don't know how to do double integrals and partial derivatives and things like that yet. So it kind of has to be that way. So anyway, is that good? Yeah, question.
I'm just thinking about the perpendicular thing that you talked about earlier.
What do you want me to do about that?
That's what I'm trying to figure out. So if it was
Well, here.
rectangles were the opposite way, so dx's, then would you rotate it this way?
You have to rotate around the x-axis.
It's possible to do it the other way. So we're using what's called the disk method. And listen, if we had like an extra 2 weeks, I'd teach you this other method called the shell method,
Okay.
which allows us to, instead of, here, I'll just draw this in right here. So here's your shape. It really comes down to a time limitation. So we have to use, I'll put it up here, it's either going to be, depending on the shape, it's going to be the disk or the washer method, which really is kind of the same thing. The washer is just kind of an adapted version of the disk method. And so, since we're using this, the representative rectangles have to be perpendicular to the axis of rotation. Here's why. I'm going to try to draw an amazing 3D drawing for you.
Oh, it's perpendicular to the axis.
To the axis of rotation.
That's what I think.
So do you see the disk that I just drew?
Yeah.
And so then, maybe you have another representative rectangle up here that you just wanted to draw in for some reason. This gets rotated around too.
Okay.
That is
So,
totally...
Like our pencil was like the axis.
Yeah, your pencil was the axis of rotation.
Okay.
And so you've got to use the disk method here. And so the disk method demands that we have a representative element, representative disk, or rectangle, depending on how you want to think about it, being perpendicular to the axis of rotation. And so just all these, watch the video again, all these little circular slices of varying radii
Okay.
is really what it comes down to.
So if you're rotating down across the x-axis, then it's dx, and it would be the other way.
Yeah. Yep. I think, is it okay if I erase all this? I can't remember, well, actually, can I do this? Yeah, so let's look at number 2. Number 2 is a really good contrast. So with number 2, it says the region is bounded by f of x equals 2 minus x squared and the x-axis. Find the volume of the solid if you revolve that region about the x-axis. And so in number 1, we revolved around the y. This will be revolved around the x. So let's use the Play-Doh again. Let's think about what this would look like. Here is my region. 2 minus x squared is what kind of a graph? And specifically,
Upside down.
upside down, moved up to, yeah, you know, you got the hand motion, yeah, you got it. So it looks something like this, right? So there's my parabola from, 2 minus x squared, bounded also by the x-axis. So my region is this, and so then that region will be revolved around the x-axis, creating a solid three-dimensional shape. So again, use your Play-Doh. Let's try to think about what this would look like and create that shape. Maybe I'll do the same thing. So there's my representative rectangle. As I mentioned before, what this does is this sets in motion everything else. This representative rectangle has a very specific thickness. What would it be? It would be dx this time as opposed to before it was dy. And so what that means is that in the end, as we work towards finding the volume of this shape, everything has to be in terms of x, not y. So here we go. I've identified the disk method. I've identified that it's volume by rotation. So I'm going to write volume equals pi integral of radius squared dx. And again, I need to fill in the details, obviously, but I'm always going to start with that framework once I identified, hey, it's a solid volume shape, and it's going to be the disk method. I always write that so that I know that I just need to fill in the details and everything else is already set. Limits of integration might be a little more challenging here. With a vertical representative rectangle, we accumulate from left to right. So wouldn't we start over here and finish right there? Question is, what are those places?
-2 and positive.
Yeah, your question, Noah?
No,
Okay. So where are you getting this root 2 thing?
I said 2 minus x squared equals 0.
That's right. So 2 minus x squared equals 0. You solve that, you get plus or minus root 2. So that is valid, right? Why would you set it equal to 0 to figure this out? Yeah, because the x-intercepts, right? That's where this region starts and stops. So I'll put negative root 2 to positive root 2 right there. And now let's talk about the radius. Doesn't the radius start on the x-axis? And then it moves up towards the, the edge of the region. So again, going back to some very young thinking, but still valid thinking, from there to there, from one green dot to the next, what kind of a distance is that?
Y.
That's y, right? So if you wanted to, you could write y there. That's a major problem as far as trying to move forward, because now we've got a mix of variables. We don't have the mechanics to deal with that. And so we say, hey, y is correct, it's just not usable. So what can I replace the y with that would allow me to have something usable?
2 minus x squared.
We already have it, don't we? Y equals 2 minus x squared. So that's what I would put. I probably wouldn't write the y in there. I would just say, hey, I realize that y equals 2 minus x squared, and just put that in as such. So to actually evaluate this, you could either math 9 it or you could do it by hand. And I'm confident that you could do either way. Can I show you something that might be a little bit of a shortcut, that might be a really helpful shortcut? Did you notice that there is a certain symmetry to this shape? Wouldn't it be fair to say that the left half and the right half are exactly the same size and shape?
Yeah.
Left half would be half the region, the right half would be half the region. Okay, so I would propose this. What if I said volume equals, I'll do this. This is going to be a slight mistake, and I'm going to ask you to fix my mistake. What if I wrote this? Integral from 0 to root 2, 2 minus x squared, squared dx. What single number could I put in to fix my little error?
2 pi.
Because didn't I just get, not 2 pi,
2 times pi.
2, right? Because didn't I find half the volume with that?
Yeah.
And so if I multiply by 2, I take my half of my volume, I multiply it by 2, now I got the whole volume, right? This only works if the figure you're looking at is symmetrical. Why would I bother?
You don't have to do the negative, if you're doing it by hand.
The negative root 2 thing,
Takes away half of it.
and specifically I've taken away the negative root 2 and replaced it with,
0.
and isn't 0 wonderful oftentimes with FTC1? Because doesn't it often make a whole term just kind of go away?
Usually does.
So, unless you're dealing with like e to the x or ln of x or something, it usually does make it just go away. So that might be a valid option for you. It's in no way is it required, but it might make it easier for you to deal with. Okay, so let's do move ahead a little bit here. I think we'll have a chance to break the Play-Doh out again. I want you to think of this as a radically different thing than the disk method, because it's really not. It's simply an adaptation of the disk method for a certain type of shape. And I'm going to have you use the Play-Doh here in just a moment to make the shape. So let's say that I've got some region. We'll come back to the formula in a minute. I'm going to draw this graph down here. Let's say that I've got some region, and it's created by a couple of graphs. Let's say, I'm going to try to make this easy on you. Let's say that the region looks like this. Let's say that I got one graph that does this, and let's say that the other graph, I don't know, does, now let's just make it really simple. Let's go with a line. Let's say the other graph looks like that. Can you see the region that would be enclosed? Highlight it right here. So then what if I took a region like that and revolved it around the y-axis? Use your Play-Doh, and try to make what this would look like. Okay? We'll talk about the resulting shape and why the washer method is the way to go here. So, would it be fair to say, guys, would it be fair to say that your shape and my shape has like a large gap in the middle?
Yeah.
Right? It does, it does close down there on the end. It is just a 1 point thick there on the very bottom of the bowl, but it's got a giant gap. Other times we're going to have shapes that have like legitimate holes all the way through them. Like you could have something like this, where there's just like almost like a donut-y kind of shape. It's got like a little hole right through the middle of it. So in these cases, we have to use what's called the washer method. And so when I say washer, I want to be really clear about this. When I say washer, I am not referring to, I'm not referring to like the clothes washer or the dishwasher that you might have at your house. I'm referring more to like a hardware store washer. You guys know what a hardware store washer looks like?
Yes.
Is it a circle with a hole punched out in the middle? It helps keep the bolts tight, right? Yeah. So when I say washer, yeah, you get a million of them, right?
You know why that helps keep the bolt tight?
Yeah, it's expansion, contraction, vibration. The washer isolates the bolt from the vibration a little bit. So, so with a washer method, like this right here, this would be a disc, right? A washer, though, would have the hole punched out of the middle, kind of like that. Does that make sense? Allowing for a hole in the middle. And so because of that, if you look, I'm going to hopefully finish, yeah, this should finish up really well. Because of that, the formula that we use essentially is pi big R squared minus pi little r squared. We'll review this when I see you again tomorrow, but the big R stands for like the bigger radius, and the little r stands for the smaller radius. And so by subtraction, all we're really doing is we are subtracting out the volume that was punched out of the middle. Does that make sense? So I'm not about to floss my teeth. I want to do a little demonstration for you, so I hope that you'll watch. So Blake, would you mind being my assistant here? Can you hold on to that? And I'm going to try to cut through this with the floss. And with the floss, there we go. You can just pick up one of those.
Wow.
Okay?
Very
And
impressive.
do it again. I know it's like the Hopefully a good demo.
Oh, the slime one.
Did I lose some of it? Well, I'll just go with this one then. So I basically cut it, and this is a washer, isn't it?
Yeah.
It's a really rough looking washer because I was like kind of wavering a little bit there. But this is a washer, kind of like you see on the screen there, right? You see it?
Yeah.
And if you take these little washers, all granted with the hole punched down the middle, then eventually you could create a shape like this where there's a big gap, like a bowl. Here's another, looks like Blake can help me out a little bit. There's another smaller washer, you know, you can see the washers that get from large to small as you move along the shape that we drew there. And thus creating a shape with a hole or just a gap in the middle of it. And we simply use the big R squared minus little r squared to accomplish that. So when I see you all tomorrow, we will explore this and probably finish it, and that'll put us in really good shape leading into next week. So if you would, with your Play-Dohs, this is really vital. This is, again, I mentioned my daughter earlier. We let her know that when you put the lid on the Play-Doh, it has to make a click. As you can hear, a little click as it seals up tightly, because if you leave it on there only halfway, the Play-Doh dries out, and the next person is like, what? It's already dried out, and they get upset. So please do put those back over there on the desk or the countertop, and I'll see you guys tomorrow. Have a wonderful day. You bet. Thank you.